So the next test we're going to go over is the integral test. So this is section 11.3. So far we only know how to actually find sum of series. So we have a geometric series, which we know explicitly when that converges or diverges. We've got these telescoping series, and then we have the test for divergence as our main tools right now, but we need to come up with something a little bit better. So what happens if that general term goes to 0, but we still don't have enough information or can't find a formula for that partial sum? So what we're going to do is kind of walk through an example. So we're going to consider a specific series, and we're going to look at the sum from n equals 1 to infinity of 1 over n squared. So the very first term would be you plug in n equals 1, you get 1. Next term is 1 over 2 squared. Then it's 1 over 3 squared, 1 over 4 squared, and then that just continues onward from that point. So we don't have a nice simple formula for the partial sum of this. So we have to find a different way to determine convergence or divergence. So what we're going to do is we're going to consider the function 1 over x squared. So we've done this to test for monotonicity of a sequence before. We're going to do the same type of thing now. And we're going to assume that our value of x is just greater than 0. So let's take a look at the graph of this function and see if we can see a nice relationship between that and our series. Here's our x values, here's our y values. The biggest this thing goes is 1 for our specific values, and we've got a half around here, and we're gonna pick some nice numbers that we could plot a little bit better. So x being 1, 2, 3, and 4. Okay. So if we go to plot these points, the very first point when you plug in 1 would go through 1, 1 up here. When you plug in 2, it'd be 1/4, which is around here. Then you'd have 1/9, and then you'd have 1/16. So this thing's going to get small pretty quick. So the graph, not the best drawer on this yet, would look roughly like this. Here's the graph of f of x equals 1 over x squared. Okay. So now let's in turn consider a few things. If we look at this line here, we could estimate the area underneath this curve with a rectangle. And so the height of this rectangle would be 1, the width would be 1. If we look at approximating the area under here, the width of this rectangle is 1 again, and the height would be the function value at 2. Same thing here, same thing here. So we can approximate all of the area under the curve by these rectangles. Each of them would have width 1, and the height would be the function evaluated at that point. So a little bit nicer of a picture under here that I'm going to bring up because drawing on an iPad is not as easy. So you can kind of see this a little bit better. So here you can see that the output or the area of this rectangle would be 1 times the function at this point. Again, the area of this rectangle would be 1 times the function at this point. Here, 1 times the function at this point. And here, 1 times the function at this specific point too. So each rectangle is going to have a width of 1, and the height would be 1 over n squared, where the n's going from 1, 2, 3, and so on, when we use that right endpoint. So if you add up all of the sums of these rectangles, you get the first one as an area of 1, then the next term, the next term, the next term, and eventually the sum of these rectangles is exactly the series that we started with. But the nice thing is the sum of our series is actually smaller. We've got all of this extra space up here. So we know how to integrate a lot easier than we can deal with some of these series. So our series is smaller than this integral from 1 to infinity, basically. So if we can see if the integral is convergent, we should be able to say the same thing about the series, okay? So if we look at the area underneath the function, excluding this first rectangle because we can't go from 0 to infinity because of that vertical asymptote, the area under the function would be done by doing an improper integral. So you go from 1 to infinity of 1 to x squared. That's a nice simple reversing power rule. So you get a nice limit that you can evaluate. And using our techniques from section 7.8, we could see that this integral is going to be equal to 1. So the area under the curve from 1 onward is 1. So, including that first rectangle now, our series is smaller than the integral. So the sum of our series is, let's pull off that first value because of this problematic one right here. And then from 2 onward, we can bound it above by the improper integral. And that's equal to 1. So this gives us our series is converging to some number between 0 and 2. We aren't going to be able to tell exactly what it converges to, but we just know it's going to be a finite number between 0 and 2. So this is exactly what the integral test tells us. So if you have a continuous, positive, and decreasing function from 1 to infinity, then if you have a series that's similar to it, if the integral is convergent, the series must also be convergent. So they kind of have to do the same thing. If the integral is divergent, then the series also has to be divergent as well. So you don't necessarily need it to be decreasing for all values. So maybe, for example, you had a function that looked like this picture right here. So it might increase for a little bit, but eventually it's decreasing from onward, because decreasing's not necessarily going to hold always, but eventually it's always going to be decreasing. What you would do to determine if it's convergent or not is you start at the value, it begins decreasing onwards. So maybe you found from 7 to infinity, the first derivative is always negative. Then you'd integrate from 7 to infinity, because that's the part it's decreasing on. So we have these 3 hypotheses that we need to satisfy for this integral test. So it's got to be continuous, it's got to be positive, and it's got to eventually be decreasing. If we can show these things and then look at that improper integral, then we can say the same thing is going to happen for the actual series. Okay? So before you apply the integral test, you need to make sure all of the hypotheses are satisfied. So let's go ahead and look at a specific example. Let's look at the series from n equals 1 to infinity of 1 over n squared plus 1, and we're going to determine if it's convergent or divergent. So the very first thing you always want to do is the hypotheses are concerned with the function themselves. We want to see, is this function continuous, is this function positive, and is this function decreasing? You need these 3 things to be satisfied to apply the conclusion of the integral test. So if we look at this, well, x squared plus 1 is never equal to 0. So f is continuous from 1 to infinity, or on 1 to infinity. So that's good. First hypothesis satisfied. Second hypothesis, is it positive? Well, x squared is definitely greater than 0 for x greater than or equal to 1, which means x squared plus 1 is greater than 0 for x greater than or equal to 1. So if you flip it, the bottom's positive, so 1 over the bottom also has to be greater than 0 for all x greater than or equal to 1. So yes, this is positive. Now, most of the time, we're gonna force you to use the integral test. So you're gonna have to show these things. So you have to actually go through some process. So you can say there's no discontinuities, it's a rational function, it's continuous on its domain, whatever you need to. But you do have to actually justify what's going on. So next, we wanna go ahead and we wanna see, is this decreasing? So we need to go through and we need to find the first derivative. We want to see, is the first derivative positive or negative? It's decreasing, it better be negative. So first, let's go ahead and take the derivative. So it's 1 over x squared plus 1. That's just applying your power rule. So you get a negative 1 down. You get x squared plus 1 to the negative 2. And then chain rule, you get a negative 2x that pops out. So our derivative is negative 2x divided by x squared plus 1 squared. Okay. So we need to do a number line to test where this is positive, where it's negative. So you want to look for two things. There's no vertical asymptotes, because that denominator is not equal to 0. And then you have a 0 when the numerator is equal to 0. So the only important point we have is when x equals 0. So we'll use that to break our number line up. We've got 0. We're looking at the derivative. You don't care about over here because the function's only really defined from 1 to infinity. If you plug in a positive number, the bottom's always positive. The top will be a negative times a positive. So the first derivative will be negative from 0 to infinity. Okay. So we can say, since the derivative is less than 0 on the interval 0 to infinity, we get f of x is decreasing everywhere it's defined. So we really only care about from 1 to infinity. Okay? So all the hypotheses of our test are satisfied, so we can apply the integral test. So all hypotheses are satisfied. So we can apply the integral test. So we want to take the integral from 1 to infinity of 1 over x squared plus 1 dx. So your techniques from 7.8 are going to come back in handy. This is improper, so you need to change the x to a t, and then you want to let t approach infinity. And you know this is my favorite function. So the antiderivative of 1 over x squared plus 1 is exactly arctangent of x. So we get the limit as t approaches infinity of arctan of x evaluated from 1 to t. So that's going to be the limit as t approaches infinity of arctan of t minus arctan of 1. And as t approaches infinity, the arctangent function approaches pi over 2. And arctangent of 1 is pi over 4. So this integral is exactly pi over 4. So what we can say is, since the integral from 1 to infinity of 1 over x squared plus 1 dx is convergent, our series has to do exactly the same thing. So by the integral test, the series we were given, so the sum from n equals 1 to infinity of 1 over n squared plus 1 is also convergent. So again, we have absolutely no idea what it's going to converge to. It's something between 0 and this bound that we got here. So something between 0 and pi over 4, but we really don't care what it converges to. We just care that it actually is convergent. Okay. So this test is quite tedious. You're going to want to use it as a last resort because we're going to have better tests that will work for a better variety of things, because not only does that term have to be integrable, you've got to go through all of these different things, and then you've got to go ahead and evaluate an integral. It's nice, but again, because of the amount of work you have to do, this will be your last resort when you're looking at a series. Try something else first, but first and foremost, you go through that test for divergence and quick look at the terms. If that doesn't work, if it does go to 0, you move on to your next tool. And this will be the one you want to put at the very bottom of your tool belt. Okay? So let's do another example so we can just get some practice with it. We want to test the series for convergence or divergence. And we're going to sum up from 1 to infinity n squared over n cubed plus 1. So first and foremost, you always want to define your function. If you do this dealing with n, you're going to have a bit of a problem. We want those hypotheses on the function itself. So first, we've got to see if it's continuous. And if you look at that, the only time the denominator is going to equal 0 is when x is negative 1. So f only has a discontinuity at x equals negative 1. So it's continuous on 1 to infinity. Okay, which is where we want it. Now we want to see, is this thing positive? Well, if you look at the numerator, x squared is greater than 0. Now we're going to keep using for all a bunch. So you can use another notation, which is an upside down a. So this x squared greater than 0 is true for all x greater than 1. So it's kind of a side note here. This means for all. So you don't have to keep writing that over and over. Then if you look at the denominator, we've got x cubed plus 1 is definitely greater than 0 for all x greater than or equal to 1. So the numerator and denominator are both positive. So when you take the ratio of these two, it's definitely going to be greater than 0 for all x greater than or equal to 1. Okay. Now decreasing. That's going to be a little more tedious because you have to take a derivative. I trust at this point that you can actually go ahead, differentiate this, and simplify it. So I'm just going to go ahead and tell you that the derivative will equal x times 2 minus x cubed divided by x cubed plus 1 squared. Okay. So after you go through quotient rule and factoring, you can find that out. So we want to see the zeros and we want to see the asymptotes. So first, let's look at the vertical asymptote. That's going to occur when x cubed equals negative 1. So one important point is x equals negative 1. Then if we look at the zeros, we've got a couple possibilities. You've got two factors, so either x could equal 0, or you have x cubed is 2. So that would mean x is the cube root of 2, which isn't a pretty number, but that's okay. So when we split up to do our testing, we want to look at the derivative. We've got a couple important numbers. We've got -1, we've got 0, and then we've got the cube root of 2. Okay. And again, this thing's only defined from 1 to infinity, so I don't care about here, and I don't care about here. Really, I don't even care what's going on from 0 to √3/2, because I care about this long piece here. If you do plug in, say, 1, then it's going to be a positive number. If you plug in, say, 3, you're going to get a negative number up here. So really, we only have f decreasing on a particular interval, but that's okay. It's decreasing from cube root of 3 onward. So f is decreasing from cube root of 2 onward. So let's just put it from cube root of 2 to infinity. So we want to apply the integral test to this. That cube root of 2 is not a pretty bound. I don't need to integrate starting from 1 to infinity. I'm only going to integrate over that decreasing part. Because it's just a finite area that's going to be on that first piece, it doesn't make a difference. I care only about this decreasing part. So now that all the hypotheses are satisfied, that's not how you spell hypotheses, here we go. Now that all hypotheses are satisfied, we can apply the integral test. Oh, that is not an A. So we want to look at the integral. You could do the cube root of 2, but I'm just going to start at 2 because that's the first natural number that occurs in that interval. And we're going to go from 2 to infinity of our function, which is x squared divided by x cubed plus 1 dx. So immediately we have to turn this over to a limit. So you're going to go from 2 to t, and then you're going to let t approach infinity. And the inside is going to stay exactly the same. So you need to do a u sub to go through this. I'm going to go ahead and show you how to change the bounds, but if you want to just do it off to the side, you can absolutely do that too. So we want to make the substitution that u is x cubed plus 1. So du is 3x squared dx. Okay, we don't have that 3, but that's okay. Just bring it over. A third du is x squared dx. Now we've got limits involved, so let's go ahead and change these. But again, you could just write equals x equals t, equals x for both of those bounds instead. But first, when x equals 2, then u is equal to x cubed plus 1. So that's going to be 8 plus 1, which is 9. When x equals t, the upper bound is going to become t cubed plus 1. So now we can change everything over for this integral. This becomes the limit as t approaches infinity. The inside becomes 1/3 over, that's just u, and we get our du. And then our bounds start at 9 and go to t cubed plus 1. So this is just a natural log. This is still our limit. We haven't taken a limit yet. We get 1/3 that pops out, and then the integral of 1 over u is the natural log of the absolute value of u. And this will get evaluated from 9 to t cubed plus 1. So plugging in these bounds, we'll take the limit as t approaches infinity. You get 1/3 times the natural log of t cubed plus 1 minus the natural log of 9. Okay? But as t gets larger and larger, if you think of your graph of the natural log function, looks like this. So this piece is getting larger and larger, doesn't matter, this is blowing up to infinity. So since the integral from 2 to infinity of x squared over x cubed plus 1 dx is divergent, our series has to do exactly the same thing because we satisfied all the hypotheses. We can say by the integral test, the sum from n equals 1 to infinity of n squared over n cubed plus 1 diverges. Okay? So this is a really nice test. What you're going to actually learn in the next section is this plus 1 really doesn't do a whole lot of anything. So if you were to ignore it, it would look like n squared over n cubed, which is 1 over n. So it's going to look like the harmonic series, which is why this thing is divergent. So we're going to have much better tests to go through this, but the integral test is something that is still beneficial, and it's where we get our next important topic from. So we get something called the p-test for divergence. So way back in section 7.8, we went through and looked at the integral of 1 over x to the p from 1 to infinity. So we call this a p-series because if you notice, you're going to have the variable to a power, so p for power. What we did back then is we knew this integral was convergent if p was greater than 1. So 1 was that cutoff point. So the integral of 1 over x squared is convergent. The integral of 1 over x to the 0.99999 would be divergent. So we get two nice criteria just like the geometric series. You get convergence if p is greater than 1. You get divergence if p is less than or equal to 1. So 1 is the cutoff because 1 is just like the harmonic series. Okay, so this is great. Just like geometric series, you have really nice criteria for whether something converges or not. So this first example, when p equals 1, you get the sum from n equals 1 to infinity of 1 over n. That's exactly the harmonic series, so it's divergent. If you look at this next one, those constants you can always pull out, but the power is 7, so p is 7. It's going to be convergent. Here, you don't need to use the p-series. This follows just directly from the test for divergence. But if you think of it as a p-series, the p is -5, and so it's going to be divergent. In this one, you've got the cube root of n, so the power is 1/3. So again, divergent. Great criteria for it. Here, our power is 1.0001, which is greater than 1, so it's going to be convergent. So the series and the geometric series have the most clean-cut criteria for convergence or divergence. So what we're going to see in the next section is that we can compare a lot of other series to these two specific ones. And based on that, we can predict that they're going to probably do the same thing. If you add or subtract some constants or you add a smaller term to it, it shouldn't change that convergence or divergence much. So those are going to be our next two tests coming up soon.